Okay, so we're going to do the input stream word counter. And the way we're going to build this code in C is similar to how we do a linked list. We're going to start our tree with the definition of what a node of a tree looks like. This is the fundamental component of a tree. And we, as people using the tree to accomplish some algorithm or to build some higher level data structure, interact with these tree nodes. So I'll call one of these tree nodes, I just wrote it in two separate lines. I'll call it a capital T node. Okay. And it doesn't have to be general. You can do it in a general way with a void pointer to some data, but oftentimes you're interweaving it into an application and you customize it to have what it needs for that particular application. So a good example here would be for this word counter, I want my tree to contain the data. Okay, so in this case, let's assume the tokens are ints. They can be char stars. It just saves me string comp versus equal sign. That doesn't make any difference. It can be any comparative function. So let's assume that each token is an int. And let's say I want to keep also a count of that token. So this isn't the tree structure, a tree node that would be useful for any type of application. Obviously, I could bundle data and count and call it void star and try to reuse something that I have already. But it's so easy, you typically don't do that. Okay, you typically just build these things on the fly. That's what's so nice about C, this recursive data structure with the pointers to instances of itself is so clever, and I don't know, it's just so slick that you just sort of do this real quickly. So I create these T nodes, and I have I'm sorry, I also have a pointer to the left and right subchild. Okay, that's the key versus just the previous and next element that you would see in a list. And I keep a count of the number of elements. So then all I really need for this code is a simple loop and a function which creates a node and adds it to the tree. Okay, so I'm going to write a function add node, and an add node will create the memory for and initialize, kind of like a constructor, tree node and return a pointer to that tree node. So this is just my regular malloc. I'm going to set the data to whatever value I want to create this T node to use. And then I'm going to set the two children to null. That's an indication that it's a leaf node. That'll be my convention. That's a natural convention. And then I'm going to say, after I create this node, that the count is one. So in other words, when I've encountered a new token, I know that token's not in my tree. So I'm going to have some operation to check, is this token in my tree? Just like the examples I showed you. I'm going to traverse the tree. And if I don't find it, once I hit the leaf node, then I know it's not there. If it's not there, I call add node. And that says the count of this is one. This is the first one I've seen. And its value is going to be whatever value I was searching for. And this function returns that node. And it is now configured as a leaf node, and it will have to stick it in the right place as the child of the correct node in the tree. But that's easy because I've gotten to the leaf node who will be its parent. So I will link its parent to it in the main code. Okay, so it's really going to be that simple. What I want to show is two ways of doing the main loop where I look for the value in the tree and increment the count if the node that represents that value is there. And I call this add node function and link it to the parent if it isn't. There's a sort of a less concise way, which uses a few if statements in a loop. And then there is a very concise way, which is recursive. And there are reasons you might want to use either, but sometimes it's just a question of preference. So let me go look at the code and we'll go over it in a few steps. Okay, so this is a very simple code. I have right here the T node that I showed you. Okay, we went over what that is. The add node function I just have here at the bottom, so I had to prototype it. The add node function is exactly what we went over. So now we're just going to go over the main loop of the code. So first, just for testing purposes, I hardwire some data. So this is the data I'm going to read, and I'm going to count the occurrences of. So you see, for example, I have 267s and 1, 2, 3, 4 ones, whatever. So I'll verify that I can do this before I do an input parser. This is really just a test run. Okay, so I'm going to create a pointer to my first node, which I'll do outside of the loop. I'm going to call that node root. I'm also going to call it node for looping purposes. All right, so let's do one outside of the loop just so we can see what it looks like. Otherwise, I would just call my add node. So root equals malloc size of t node, and I create memory for it. Root.left equals root.right equals null. That indicates that root is the leaf of a tree. There are no subchildren. Root.data equals data 0. So I'm going to stick the first data element in. This is critical. The way that you build a binary search tree is not unique to the list of values you're giving it. It depends on the order in which you insert them, right? So for any particular list, you can find the optimal way to insert it such that you have the most balanced tree possible, but you don't do that normally. You either hope it's going to be balanced or you have fast ways to balance it, which I'll talk about later. Okay, so I'm sticking the first element in the root node, and I'm going to set the count to 1. So I'm doing what add node's doing. I'm just showing the steps here just to remind you. Okay, then I'll just add the others from that point on. So I'm going to loop over all n elements of data, starting at element 1. Element 0 has been done already. And now I'm going to say node equals root. So I'm going to start at the top of the tree each time I go through this, okay? Because I've got to start at the top to find the place to put it. The token I'm going to look for is data 1, the first element of this input data array, and I print it just as a test. And now the way I'm going to do this is I'm just going to say loop forever, and then I have break conditions. That might not be your style, but it doesn't bother me. Okay, so just look at the different conditions. We're going to sort of traverse the tree and see where to put the data. So first condition to check is, does the current node have the data? In other words, is it in root? If so, just increment the count and then break, you're done, okay? If not, then if the value is greater than node.data, you go, let's see, if node.write is null, so it's one step more complicated, I remember. So if node.write is null, so in other words, if there are no children, you've got to add a write node and put the data in. Okay, so node.write equals add node val. You create the node, then you stop. Okay, so it's the right root. Let's say the number was 20. It's the right child of root, and you add it, and you're done. Otherwise, if it's not null, then now the new node is node.write. Okay, and that brings you back up to the top of the while loop, and you check whether that node has the data, right? Because this is else if. So otherwise, you do the same thing with node.left, okay? So val is less than null.data. If it's null, you have to add the left child. Otherwise, node equals node.left, and that's it, okay? So if you just go through one more iteration of this, node.left will be the new value of node in the while loop, and so you have to ask, node is val node.data. If so, you found it in the left subchild, or the left child, I'm sorry, and you just increment it. Otherwise, you see where to go from there. Okay, and you go all the way until you hit a leaf node. And when you hit a leaf node, you're going to be calling add node, right? And by definition, because node.left is null or node.right is null when you have a leaf node. And so you add it to the tree. So in many of these, you're just adding to the tree, but then when you encounter it again, you increment it. Well, the idea is if the tree came out perfectly balanced, then you would only need to search log n levels of the tree in order to find the value. If it's, you know, let's say once you have saturated the tree to the point where many of the words that you're seeing are ones you've already encountered, then if it were perfectly balanced, instead of having to look through a whole list or having to sort something, which you can't really do because you're just traversing at one time, you just have to do log n operations. Well, obviously, if you get very unlucky, it's going to be some number much bigger than that. But what, you know, if you got really unlucky, it would just be like a linked list. But in practice, that's not going to happen typically. That said, there are maneuvers you can make within the tree that are quite simple, if a little tedious to code, that can preserve its binary tree structure and ensure that that doesn't happen. Okay, in fact, they can ensure the bounds on the height of the tree are quite tight and asymptotically log n. But even without that, this can be a simple version that's going to be very useful because in practice, that's often unlikely to happen. Okay, so if we want to try to run this, and I didn't, so I'm not sure what's going to happen. Let's try to compile it. Oh, there you go. It's unhappy with something. Let me just pause and check that error because I forgot to test it. Okay, I just misspelled type def. So now if I compile it, compiles. And if I run it, boom, so it finds the second occur. Every time it finds a new occurrence, it just tells you. So this is all when there's a repeat. So 2 occurrences of 1, then it found the 3rd occurrence of 1, then it found the 4th occurrence of 1 that we saw. Found the 5th occurrence of 3. So the point is, if you want to count the number of words, or if you want to find a word that, or in this case, an int, but this would more typically done for char star, you can do it potentially very efficiently with this kind of algorithm. So the other thing I wanted to show you was the same thing, but recursively. Okay, and it's a simple recursive algorithm. And the advantage is that it is just much less code. The disadvantage is in practice, recursive algorithms, the way that you sort of replace having to build a stack or do some stack type looping structure manually with having the stack be controlled by the runtime. And that can not be in practice always very efficient. Okay, but in this case, I think it's fine. So we have the exact same code. I have a tree print function also that I wanted to show how to do recursively, but I'm just going to show the same add tree method. I'm just going to show the, let's see where my main method is. Yeah, so I did this a little bit differently. I wrote a recursive add tree method. Okay, so I'm going to loop over the input data, grab the next value, and I'm going to call node equals add tree node, and the add tree function is going to recursively add that node. Okay, so when it does it recursively, it starts by asking if you're at the new location of insertion, then do all the regular things to add a new node. Otherwise, if you found the data at that node, just increment the counter. Otherwise, these 2 simple recursive expressions replace what were those funny conditionals that I showed you before. So if the data is less than the data in the current node, then you recursively call add tree on the left subchild. Okay, so in other words, you pass the left child back into this function, and you repeat the process with the left child, and similarly for the right child. And if you track this, what it'll eventually do is keep building up a function call stack until you get to the leaf node. And when you get to the leaf node, it will return P all the way through that call stack once it finally gets to this line, once it passes these other lines. Or it will get to P.count, and it will return P through the call stack, and it will accomplish the same thing I showed you on the other side. And the other thing I want to show you is there are lots of simple ways to print a tree. There's pre-order, post-order, in-order, and these things can be expressed recursively very nicely also. So if you want to look at the state of the tree, it's not going to print it hierarchically, but it will print it in a way that you can easily reconstruct what the hierarchical format looks like. You can do simple recursive functions like this. So the tree print function can just say tree print, print out left, then the print statement, then print out right. Or you can do it in various different orders. I'll talk about that in a minute. Okay, so if you find the recursion, I mean, it is very elegant. To me, it doesn't really make that much of a difference, but these things lend themselves so much to recursive implementations that it's important to understand them and be able to sketch that code very easily, whether or not you actually want to use it in practice. Okay, now we're going to talk about some more nuanced issues in the next segment.